Okay, next step. We've already learned how to use the equation for the electric field due to a point charge to find what the electric field value is at a point somewhere distant from some point charge. Now what we're going to do is investigate 2-point charges and find out what the electric field is at a given point based on those 2-point charges. Now the first thing is I want you to be able to visualize the electric field in all the points of space surrounding these two charges. Of course, calculating them all at the same time is a whole different issue, but intuitively you should see how these electric fields play out. As we can see, the charge of Q1 has a greater magnitude than the charge of Q2. So Q1 is more negative than Q2 is positive. So we can see that the influence in the space around the two charges should be more due to Q1 than to Q2. And in fact, what we see is something that looks about like this. You can see that field lines are leaving Q2 and entering Q1, but more field lines are entering Q1 than are leaving Q2. And this is because if we are looking in the area around the two charges, we can see it warped, the electric field warped by both charges. But if you zoom out, then you can see that overall the net charge here would be negative 80 nanocoulombs overall once everything is added up and said and done. And therefore, far away, it would look like a negative 80 nanocoulomb point charge. And so we should end up with extra field lines coming in toward our system, right? Okay, so that's just kind of the intuition on this. Now what we can do is make a calculation. Now, if you're not familiar with the principle of superposition, then let's go ahead and discuss it. Superposition basically is a quality of many of the things in physics, which allows them to simply be added together. The influence on a vector field due to one charge can be added to the influence of the vector field on the other charge. Of course, since it's a vector field, we have to add them as vectors. We cannot add them in a scalar fashion. So let's find a point to discuss, because really this calculation is about one point in space that we call a point of interest. And it could be anywhere. Where? Let's say this spot right here. Okay, so we have a spot chosen. We'll label it point P because, it's a point. And sometimes what I like to do is put a little X over it so that you can remember that this is simply a point in space and is not itself a charge. All it is just a little chunk of air that we're analyzing. Or out in outer space, it would just be a chunk of missing nothing, right? So this is not actually a charge. It's just a place that we're staring at, right? And we want to know what is the electric field at that spot. So the first thing that we're going to do is erase the influence of Q2 and only analyze it from a standpoint of Q1. So let's go ahead and find what the electric field is at point P due to the presence of Q1. Now we already know our equation, so let's go ahead and start putting it together. The electric field at point P due to charge 1 is going to be, first of all, we want the magnitude. Always find the magnitude first. So we find the magnitude, and it's going to be, of course, equal to KE Q1 over R squared. And I'm going to put a little subscript 1 on our R to represent that the R that we're talking about is the length from Q1 to our interesting point. It's only interesting because I said it's interesting. There's no other reason that point is interesting. Okay, so let's draw an arrow. So here we have R1 in our equation. And we need to draw our arrow according to the electric field direction at point P due to the presence of Q1. We know that electric fields go toward negative charges and they go away from positive charges. So let's go ahead and draw ourselves a green arrow. And it doesn't really matter how long the arrow is. Our other arrow that we draw from the next charge will be representative of the relative strength of the E field to this particular arrow. Okay, the important thing is that we know what the direction of that arrow is. All right, let's run our calculation. First of all, we're going to need to know what R1 is. Down here, I will write what R1 is. We know that this is in units of centimeters space-wise, and so, or length-wise. And so if we know that the distance between Q1 and point P is 7 horizontal, oh wait, no, it's 6 horizontal, there's the overcounted there, 6 horizontal and 1 down, right? And therefore, our R1 distance should be the square root of the horizontal distance squared plus the vertical distance squared, or 0.06 meters squared plus 0.01 meters squared. It'll probably be somewhere around 6, because I mean it's almost 6 centimeters, right? And that gives us 6.08 centimeters. I converted back to centimeters. When I punched this in my calculator, I got 0.0608 meters. And so I'm just kind of writing that in a little bit of a simpler way. Okay, so we have R. We know what Q is. Q1, I have a capital Q here, but really, like I've told you before, there's nothing special about this being capital or lowercase. So in this case, our Q1 is going to be equal to this Q. And then, of course, we know our constant. So let's go ahead and write all this out. We have Coulomb constant. We have our charge value. And we have our distance squared, which I will put in terms of meters again, even though I've written them in centimeters here. And remember, that's because when we do our calculations, we want to make sure that we don't end up with an incorrect conversion to SI units. So it's always helpful to kind of put this in meters before you run your calculation. The value that I get for this is 340,000 newtons per coulomb. Okay, now we don't really have a lot of information about direction on this, but we do have some information on the magnitude of the field here. Let's go ahead and break this down into components so that we can truly look at the electric field due to point 1 as a vector. The first thing that we'll need is the electric field due to point 1 in the x direction. And now in order to do this, I always like to draw out my triangle. So I'm going to draw our triangle here off to the side. It looks something like this. And recall that we have an x component here and a y component, like so. We can see immediately that the x component is pointed to the left, the y component is pointed upward, which means that our x component is going to be negative valued and our y component will be positive valued. Now, how do we know what the angle is here? Well, we have already created a triangle here that is a similar triangle to the one that we have here. And by similar, I don't just mean, hey, it looks like it. I mean, it is mathematically a similar triangle, which means that they have the exact same angle. So if we wanted to find this angle theta, I'll call it theta 1. What would theta 1 be? Well, we know that the opposite side of this triangle is 1, and the adjacent side is 6, and that should give us the ratio that defines theta 1. So we know that the tangent of theta 1 is going to be equal to 1 over 6 by our tangent ratio. We can then write that theta 1 should be equal to the arc tangent of 1/6, 9.46 degrees. So now we're interested in the x component, which is along this part of our triangle, or the adjacent side, and so we're interested in 340,000 newtons per coulomb times cosine of 9.46 degrees, which will equal 335,000 newtons per coulomb. In other words, most of the electric field is in this direction. We can also find the y component, and that is given by 340,000 newtons per coulomb times the sine component, or 55,900 newtons per coulomb. We can write now our vector E1, and it's given as negative 335,000 newtons per coulomb in the x-hat direction, plus a positive 55,900 newtons per coulomb in the y-hat direction. Okay, now we have all of this available, but in order to save space, I'm going to go ahead and get rid of our calculations in the middle and only put the answer. And that completes finding the electric field due to only charge 1. We can repeat this process rather simply for charge 2. Let us find the magnitude of the electric field due to the presence of charge 2. Now, again, we're going to be interested in locating the radial line here and finding an arrow that represents the electric field due to this charge. Okay, so I have my triangle here, the same as we had before, with my new theta 2. I have the arrow that is represented. Notice that it's smaller than the previous arrow. I have my R2 drawn from my charge Q2 to the point P. And I've already gone and calculated the radius from charge 2 to the point of interest by using the Pythagorean theorem and our 5 vertical versus 2 horizontal. And I've already calculated the angle as well. So it's the same process we did before. So we can go ahead and write out our angles, and we can go ahead and write out our variables. We've got the Coulomb constant, and we've got our charge value, and we have our calculated radius. This results in 186,000 newtons per coulomb of magnitude of electric field. Again, we can break this up into x component and y component. This is the part that I want to really spell out because this is the part that we have to be careful about. For the x component, this is our x component right here, and so we're interested in the adjacent side or cosine. And recall the angle that I calculated there for theta 2 is 68.2 degrees. 69,000. And we know that this is positive because it's pointed to the right. Same process with y. 186,000 newtons per coulomb by only our vertical component, so sine 68.2 degrees. 173,000. Okay, so we can now write our vector. The electric field due to the presence of charge 2 at our point of interest is given then by a positive 69,000 newtons per coulomb in the x-hat direction and a positive 173,000 newtons per coulomb in the y-hat direction. Again, I'll move this up so that we can observe everything together. If we bring in our first calculation, we're now ready to see the influence of both of them together. Now, this is just like the vectors you learned in Physics 1, in that if we add tip to tail this vector due to this charge and this vector due to this charge, then we should get something that's pointed off in the sort of up-left direction here. Let's mathematically add them together. We have the entire E field now, which will be the sum of the individual E fields provided by these charges, which gives us, in the x-hat direction, a negative 335,000 plus a positive 69,000, and in the y-hat direction, a 55,900 plus also a positive 173,000. Negative 266,000 newtons per coulomb in the x-hat direction, plus 229,000 newtons per coulomb in the y-hat direction after correctly adding sig figs. So that should give us then a triangle that represents, let's go ahead and add vectorially, graphically, tip to tail. And if we did so, we would end up with a point that's probably somewhere around here. And that does, in fact, look a little bit like what we expect. It's over 200 and almost 270,000 to the left, and up about 230,000, which means it's a little bit more left than it is up, and that's exactly what our graph shows us the effect to be. And if we take a look at the overall electric field that we saw before, then you can see that it actually matches quite well with that as well. Okay, so hopefully this clearly lays out the process. It's very similar to looking at the force on a charge due to the presence of two other charges, and the reason for that is that you could take this result that we have calculated and multiply it times any charge that you want to place on point P and find the force at that point. This process can be extended to 3 and 4 and 5 and as many charges as you feel like calculating. All you have to do is simply add up the effect of the x components of as many as are present, and then follow suit with the y components of as many as are present. Okay, and I know that this one is kind of tough, along with the multiple force concept, and so if you have any questions, please contact me, because this takes practice. Also, make sure to do the practice videos. Next, we're going to go into a little bit about the electric dipole, and also try to increase the intuition just a little bit.